Okay then, so now what we want to do is have a look at some of these kind of Okay then, so now what we want to do is have a look at how these ideas of for all and there exists, these notions which we've just obtained some results about how they work in general in set to the power of c. Well, now what we want to do is to actually have a practical example where we can really compute these things. So we're going to go to our normal kind of source for examples, this category of functions, or if you like, this category of bouquets. And so here we have a bouquet A and a bouquet B, and we're computing this bouquet B times A. And then, as shown here, I have a sub-object R of B times A. And of course, we can think of this as an inclusion monic, a kind of inclusion monic, little r, from an object, capital R. Now, the question is, what is for all AR, and what is there exists AR? These are both going to be sub-objects of B, but what do they look like? This is what we want to compute. So let's start with the second one. There exists AR. What does that look like? Well, firstly, let's visualize this in another way. Because you see with this R here, we're essentially selecting some of the loops and some of the vertices of this product, B times A. So another way we can draw this product is like this. So this is the kind of view of it as a function. So it's this function that sends the vertex set of B times A to the loop set of B times A. And you see with this red stuff R, we're kind of selecting a subset of the, whoops, okay, so in order to understand this kind of stuff, it's quite helpful to take another kind of view of what this stuff looks like. So this is the sort of view of B times A and this sub-object R of B times A in terms of bouquets. But of course, we can always picture these kind of things alternatively in terms of functions. Okay, so we can think of B times A really as this kind of function, B times A of S, from the set of loops, B times A of E, to the set of vertices, B times A of V. And then this R here, well, we can think of this as sort of selecting these a red subset of the loops and a red subset of the vertices in such a way that this kind of family of subsets is closed under our actions. So in other words, a loop which is in R always gets sent to a vertex which is in R by our mapping. So it's nice to visualize it like this because we can easily see which kind of pairs of a loop from B and a loop from C are in this relation R. So in particular, this loop I is in this R relation with this loop C. And also this vertex 1 is in R relation with this vertex 1 dash of A. And this vertex 2 is in this R relation with this vertex 1 dash as well as this vertex 2 dash of A. So we can picture those kind of things more more readily in this kind of form, I feel. Anyway, now it's time to actually compute these kind of sub-objects of B. So let's start with the second one. There exists a R. Well, actually, I'll just show you the answer for a start. This is the answer. It turns out there exists AR is in fact the full subobject of B, whereas for all AR turns out to be the subobject that only contains this vertex 2. But the important thing is really how we compute these things. So let's look at there exists AR for a start. So from our previous result, we have that the collection of E figures of for all AR, I mean, of course, we're thinking of all of these sub-objects as inclusion monics, but anyway, we can think of this, we can think of this set of E figures of for all AR as the set of E figures beta of B such that there exists an E figure alpha of A with beta comma alpha in this relation R. So in other words, so we have that beta comma alpha is a member of capital R of E. So then we can see immediately that since there exists this little c in A of E such that I comma C is in capital R of E, that means that I is going to be an E figure of there exists a R. Okay, so in other words, because there is something in our relation to this loop here of B, in particular there is this loop C, that means that this loop I here is going to be in there exists AR, okay, because this is obviously going to be a sub-object of B, right? And this loop's going to be in it because this loop is indeed in this R relation with this C here. In a similar way, there is this 1 dash which is in R relation to this vertex 1 here, so that means this vertex 1 is in there exists AR, and also there is this 1 dash which is in R relation to this vertex 2, so that means that this vertex 2 is also in there exists AR. Okay, so that in fact means all of the vertices and loops of capital B are in there exists AR. So there exists AR is in fact the full sub-object of B. So I've sort of argued this in more detail here. You can pause the video if you want to go over this. Anyway, that's basically how we work out there exists. The other thing to work out is for all. Okay, so here's our important formula for working out what happens with for all. We have that the set of E figures of for all AR is going to be the set of E figures beta of B, which is such that for any action, well, let's say for any arrow S at all, which goes out of capital E, so say for any arrow S from E to V, for any V, and also for any alpha dash in A of V, we have to have that the result of doing this S action on beta is going to be in this R relation with alpha dash. Okay, so in other words, what we're saying is that an E figure beta of capital B is only going to be in this for all AR sub-object thing when it has the property that whenever we do any kind of action on that kind of beta, that result is going to be in R relation with everything in A, which has the appropriate type. Okay, so it's rather a strong condition, really, is this for all AR thing. And so let's now check, like I've illustrated here, that the only thing that's in for all AR is this vertex 2 here? Well, why is this vertex 2 in for all they are? Well, if we have a look at the picture, we see that vertex 2 is in this R relation with every vertex of A, okay, because 2, 1 dash and 2, 2 dash are both in R. But what about if we do an S action on this vertex 2? What if we do some action on it? We've converted it into a different type of figure, then that type of figure would also have to be in this R relation with everything of that kind of corresponding type in A. But this actually doesn't matter in this case because there is no kind of action that you can do on a vertex in a bouquet apart from the kind of identity arrow, which, you know, we've already, you know, we don't really need to consider that again. So there's no way to, you know, convert a kind of loop into a different kind. There's no way to convert a kind of vertex into a different kind of figure by doing some action or something. So when we're just dealing with a vertex, yeah, we can just say, well, it's in R relation with every vertex of A, so that means it must be in for all they are. So that's why we have that vertex 2 is in for all they are. How about vertex 1? Why is that not in for all they are? Well, the reason for that is that basically we don't have 1, 2 dash in R. Okay, you see this is not in R. So vertex 1 is not in R relation with this member 2 dash of A, and therefore vertex 1 is not in for all they are. And if you want to say it fancy, in a fancy way, you could say, well, if we do the and if you want to say it in a fancy way, you could say, well, if we do the identity action on 1, then that thing will not be in R relation with 2 dash. And therefore 1 is not going to be in for all they are. And then finally, what about this loop? Well, this loop isn't going to be in for all they are either, because you see there's this loop B that's not in R relation with I. So I is not in R relation with, it's not even in R relation with every loop of A. So it's definitely not in for all they are. So there we have it. We've finished this computation, and hopefully this has shed some light on how we can understand these ideas of for all and there exists in general.